So when you're doing electronic interfacing, there's a couple of ways you can do it, as we discussed. However, you want to do it in a way where you do maintain some redundancies and that you do set it up for the best reliability and take into consideration what are called limp modes. Limp modes are basically modes that when a fault is detected, whether it's low oil aeration, overheating, hot protection, and reduced power, and we'll talk about reduced power a little more in depth because it really is a big one. How does the vehicle react? Is it going to get you home, and is it going to remain safe? So early on, what we realized about the JK is everything is integrated, and Chrysler has done this for many years. Chrysler back in the mid-90s, I remember, came out with their L-Class cars that had their high-speed CAN bus, and it was really a nightmare. They ran the CAN network through everything, and it was serial, so if you had a failure in one module, it could take out the rest of them. I remember replacing ABS modules to fix coolant temp gauges, and customers just didn't get that. But that's what can happen with a CAN if it gets corrupted or it's not operating properly. So the JK is very CAN dependent, as we all know, and in 2011 they really stepped up the CAN. In 2010 they changed a lot of things, and then in 2012, of course, we went to the Pentastar, and that really added a lot of CAN integration. The high-vac controller and a bunch of other functions are now CAN. So to the CAN's advantage, we can use it to operate things. If it's on the CAN network, we can pretty much control it. Now, in the early JKs, if it did not sense a RPM signal, for example, the computer would say, why should I activate air conditioning, cooling fans, charging system, ABS? And it wouldn't. So if you tried to throw an engine into a JK and you didn't have a valid RPM signal into the network, all those functions wouldn't work. So this was a problem. Unless you wanted to build a buggy and ditch all that stuff, which a lot of guys, of course, did. So early on, we built a crank trigger wheel for RPM, and it worked pretty good. Actually, it worked great. I'm still driving one on my Jeep 8 years later. But there was a lot of costs involved with machining and precision, and it just became apparent that we needed to electronically interface that. But at the same time, we said, what if there is a failure? Let's say we do go full electronic interface, even a CAN interface, and there is a failure. We want to make sure that everything continues to work. The GM powertrain goes into a limp mode and you drive home. And therefore, we started separating functions out, like charging system, cooling fan. We integrated those into the GM side, and by doing that now, if there is a Chrysler network failure, the GM side takes over and you continue to run. And we all know that the Chrysler network is not very reliable when you compare it to the GM network, especially the TIPM. The TIPM is a gateway module, and it is it's susceptible to failure in the early JKs and even in the newer ones. So we have to keep that in mind. We don't want to just do an electronic interface because we can. We have to think, what is the most reliable way, the safest way, and of course we want to gain efficiencies for cost. So over the years, that's what we've learned. We've learned how to keep these things reliable. And I mention this Jeep because this Jeep was kind of at a turning point where we had the ability to interface almost everything electronically. The coolant temp signal, oil pressure signal, RPM signal, air conditioning signals. And we've processed the air conditioning signals on these within a few months of doing JK swaps, where we actually looked at evap temperature and then cycled the compressor based on the evap temperature, and we also controlled it based on condenser pressure. That's AC condenser pressure. We have the ability now to do AC idle bump and some other things. So the question became, just because we can do an electronic interfaces, do we want to? And the answer was yes for some things and no for other things. And that's kind of where we're at right now. The module is very well integrated, and our hybrid MoTech module with CAN is capable, a lot more capable of what it's actually being used for. For example, coolant temp. We've supported coolant temp for about 4 or 5 years, where we don't have to run a redundant sensor. But in the kits and the way we were doing things, it was easy to just add a redundant sensor. It's dead reliable. If the CAN network were to go down, for example, the cooling fan on a lot of our early builds ran off of the JK computer, because the JK computer, actually the TIPM controls the fan, uses some logic like vehicle speed and trans temp. So we wanted to take advantage of that. And if we had an electronic interface that failed, we would lose our coolant temp reading, and then our fan wouldn't be controlled properly. So there, a dumb sensor, a hardware-driven sensor might make sense, and it did. And the sensors cost $20 or less. So if a sensor failed, you replaced it. If your interface failed, you're kind of screwed. So these are the things we have to keep in mind, and not just go gung-ho on full electronic interfacing. And in a way, if you wanted to keep it as simple as possible, you would probably go with redundant everything, because each network would then operate exactly the way it was intended to, and if there were a failure, it would be easy to repair by just replacing that component. By adding an additional component, a processor, bridge, interface, whatever you want to call it, and that fails, then you're introducing another failure point, which we don't want to do. So what we have steered towards the last couple of years is integrating everything on engine performance into the GM side. That means air conditioning control, idle bump, coolant temp, RPM, and we've driven our tachometers. I think this one still has a trigger wheel because it's so old, but for a few years now we've driven our tachometers electronically through the GM side, and it's pretty bulletproof. But the reality is we've learned, and we set our swaps up now, so even if you were to lose a tach signal, and this holds true for a GM or a Jeep also. Jeeps had issues where debris would get into the flywheel, contaminate the signal, and then the Jeep would stop. Well, in our case, if you lost an RPM signal, the LS would continue to run, and the LS does have its trigger wheel inside the crankcase, so it's not external and exposed to the environment. And that was one of the reasons we developed our crank module, which by the way is available standalone, and it is available in several different trigger patterns, 24, 36, 60. If you're interested and you're doing a swap on something oddball like an early TJ, and you don't want to run the crank trigger wheel. So what we've done is we've migrated away from the JK controlling the critical functions like cooling fans and charging system, and we've given that over to the GM. At the same time, we've added the functionalities to the GM side that it needs to make smart decisions. Like the BCM is integrated into the GM network for a lot of different reasons. It's not just switch inputs like from cruise control and tap shift. It acts as a power mode module and actually has some input on charging system goals and security. So we want to try to maintain that and keep it as pure as possible. So I know this is a complex subject, but we're going to talk more about it later. Right now I'm going to talk about reduced power modes. Early on, GM did have some issues with reduced power modes. Reduced power modes are usually related to the TAC, throttle actuator control system. And in the Gen 3 motors, the throttle actuator control system was somewhat different and not as reliable as the Gen 4s. There was what was called a TAC module, a throttle actuator control module that was independent from the computer. And this module was pretty much matched to an ECM and a pedal. And if you did not have the proper combination, it wouldn't work. Not only that, this module was not sealed, so if moisture got into it, it would throw you into reduced power mode. And they're extremely sensitive. Ever since the runaway throttles on the Toyotas and the Audis, manufacturers have got really tight on reduced power modes. So they might have gone too far. And even if you have a battery that's going bad, and we see this all the time with the Optimas, when the ground and power distribution sides of your electrical system are not well separated. I'm going to turn on my defroster here. the GM side will pick that up and throw you into a reduced power mode. And I'm going to try to explain reduced power modes because this isn't just something that's in LSs, it's in other manufacturers' operating systems now. The TAC module in the Gen 4s is now integrated into the E38 in the Gen 4 modules. In the Gen 5 it's integrated also, but in a different way. And these TAC modules, there's multiple modules inside the E38, and they actually talk to each other. And if, let's say, it senses that there's an anomaly or something, a rationality, the ECM will do several things. It can go into reduced power mode, and there's several levels of that, or it can actually shut itself down. Like if you have ever got a P0606 internal processor fault, and there's others, if the TAC module is sensed as being corrupt, the ECM will actually commit suicide. It'll shut itself down, and there is no recovery. You have to replace the ECM. And it's very rare for that to happen, but it does happen if guys mess with the throttle curves. If you go in and try to program the ETC tables and you don't know what you're doing, and because ETC is also linked very closely to airflow and running a mass sensor, not speed density. GM knows with the throttle body open so far, the engine at a certain RPM, and the map sensor reading X, that the throttle position should be at a certain position, and if it's not, it'll throw a math rationality code and put you into a limp mode. So there's all these different limp modes, but essentially they all do the same thing. They reduce power. Now, reduced power could mean just a slight loss of power, and you may not even know it. It may drop you down to 45 miles an hour and no faster, so you don't have a dead pedal. You can actually drive, but you have greatly reduced power. It can shut you down to an idle, where the engine will just simply idle, but you can't accelerate. That's usually what happens when you're in hot protection. Or it happens sometimes when you're in hot protection, depending on how hot it is, where you have a dead pedal but the engine's running, and in other cases it'll just shut the motor off. So there's multiple reduced power modes, and the computer will determine which one to go into. Now, what causes reduced power modes? Well, there's airflow, like we just discussed, but more often than not, it is an electrical issue with wiring, conductivity. GM early on did not run a lot of redundant grounds. Ground distribution is very important to modern computers. In the early days, this is going to be a long talk. In the early days, it wasn't required to have extremely precise ground distribution, because when you were running an O2 sensor on a 1978 Cadillac, the case of the O2 was grounded, and that was good enough, because all the O2 is a voltage generator, and it put out millivolts, 0 to 1,000, but the systems back then were so primitive, they went into open loop when you came to a stop. There were no heated O2s. It didn't need that precision. And the same thing for the other sensors, like the map sensor and the baro sensor, if it had it, crank sensor. Well, as time went on, manufacturers realized they needed more precision control. So they added what they called low reference. And low reference is essentially a ground supplied by the computer. And by the computer supplying the ground to the sensor, it then has a better internal reference, especially when working in very low current and low voltage signals. Like the O2 sensors are 0 to 1 volts, so that's 0 to 1,000 millivolts, and very, very low amps, milliamps. So we need precision ground distribution in order to handle that. At the same time, for safety, we run redundant sensors. Your APP, accelerator pedal position sensor, or as most of you know it as the gas pedal, has a couple of sensors inside of it, as does the throttle position sensor. In the old days, I remember working on the old tune ports, we had one throttle position sensor, and if it went bad, it went bad. Today we have 2 throttle position sensors, and it's kind of unique. What they do is they run these sensors off of a single ground, dual power, and 2 signals that are opposite of each other. So one goes from 0 to 5 and the other goes from 5 to 0. They both have a 5 volt reference, but they share a ground. And you say, why do they share a ground? Well, if the ground were to get weak, let's say you had a bad connection at the connector of the throttle body, or or at the computer, the low reference wire of the computer, the signals would spread apart because they work in opposite directions. So as the ground got weak, the signals would separate. Usually at about 2% over a specific amount of time, you go into reduced power mode. Same thing with the throttle pedal. Throttle pedal, low reference, gets weak, signals are going to separate, and boom, you go into reduced power. So it is critical that you, a little windy out there, it's critical that you check your grounds carefully. GM did actually have to add grounds in the early Gen 4 trucks because they determined that some of the connectors they went through, even though they were good connectors, just a couple of, not even corrosion, but if you have more than 5 ohms, that may be enough of, this is hard to explain without using numbers, but basically if the connector didn't have perfect conductivity, 0 ohms, that's the opposite of infinity, then over time you would go into reduced power. And these mysterious reduced power modes were popping up, and GM realized that they had to beef up their ground distribution. So when we build our harnesses now, in the early days we actually added redundant grounds. The transmission, the ECM has two independent grounds, including the case of the computer itself. The engine has at least 3 grounds going to the block that are shared and redundant, which means if one ground were to go bad, another ground would pick it up. The problem with the Optimas we found is that the ground distribution breaks down internally. And I get guys that say, I'm going into reduced power, and they don't understand how replacing the battery will fix it, but it does. It's because the separation between your power and ground distribution in the battery is not as good as it should be. So first thing I'm going to tell a customer with reduced power is, like in weather like this where it's damp and it's cold, pull all your connectors apart and check for moisture. If there's moisture in there, use some contact cleaner to dry it out. Put some dielectric grease in. Dielectric grease is not a conductor, it's actually an insulator, but it keeps the corrosion away. So you're going to put that in there, and that'll dispel moisture from that connector. The second thing you're going to do is check the pin contacts, especially the small tiny contacts on the ECM and the gas pedal. Sometimes the pins get pushed out, bent. In the early days we used Molex connectors in the interior, and the Molex connectors worked great for a couple of years, but down in like Galveston, Corpus Christi, Florida, corrosion would build up. The Molexes, at least the less expensive ones, don't run gold-plated connectors, and corrosion would build up. Those would throw you into reduced power. So our early customers, we recommend you just cut those connectors out and bypass them. Today we're using a spiral lock connector that's weather sealed and has gold contacts, and we've had no issues with them. So you're going to want to check that. You're going to want to check your grounds on the battery and the block, the chassis. Remember, just because the throttle body is getting a low reference from the ECM, if the ECM is not getting a proper ground from the battery, then that will throw you into reduced power too. So even though you have a good connection between the throttle body and the ECM and the throttle pedal and the ECM may not have a good ground connection to the battery, and that again is going to throw you into reduced power because of the asynchronous signals from the APP and the TPS. So you want to check those grounds carefully. If you know how to do a voltage drop, do it. Voltage drops are only valid if you do it while you're under a load. So crank the vehicle and start it when you're doing voltage drops. And you want to see, obviously you want to see 0. Set your scale on the lowest scale you have. If you have a 1/10 of a volt scale, do it. If you have a 2/10 of a volt scale, use that. But you want to see the minimal amount of voltage on a voltage drop possible. On a high amperage circuit like the starting circuit, if you were to do one across the battery cables, you might see a 1/2 volt or even 1 volt. I think 1.5 volts would be the maximum, but you're putting 250 amps through that circuit, so 1 volt can be expected. On a circuit like an O2 that's using just a few milliamps, any voltage drop is really not acceptable. So I hope that makes sense. To to avoid reduced power modes, you want to make sure the integrity of all your wiring, your power and your ground distribution, and all the connections at your computers are tight and solid. And you should not have reduced power modes. We had early reduced power mode issues exactly that coincided with GM's reduced power mode issues, because we were using GM's power and ground distributions. And in 07-08, GM started to beef up their grounds, update their computers for like P2138 and the software for diagnosing it. Excuse me. And we paralleled GM, and as they eliminated reduced power modes, so did we. We don't want to go too far and eliminate reduced power modes, because they're required for safety. So it's a double-edged sword. Now, when it comes to airflow, this is another area we have to be careful. And I know that there's a lot of LS swaps going on right now, and the Gen 4 LSs are very dependent on a MAF, or a mass airflow sensor. The Chryslers are not. Chryslers don't run an airflow sensor in general. They run what's called speed density, which is basically a manifold absolute pressure or MAP sensor on the intake. And that tells the computer what the intake vacuum is, and when the computer combines that with engine RPM and other coolant temp and ambient temp and all that, it can use a lookup table to determine what the airflow is. So it's calculated airflow versus actual airflow. But with the GM running a MAF sensor, they have the advantage of being very precise in fuel delivery. You go to high altitude to low altitude to high altitude. The speed density systems don't really keep up, because if you go from 4,000 to 12,000 feet with the same ignition cycle and you don't have a independent barometer, which most of these newer vehicles don't, they take their barometer reading at key on, then you're basing your fuel calculations on the incorrect air density. So it is recommended every 4,000 feet on a system like that, where you don't have an airflow meter or a barometer, to shut the vehicle off and then restart it to get a new barrel reading, so the fuel delivery can be more accurate. So, getting back to the airflow and reduced power, GM knows what the airflow should be, and if it's not what it should be, it can do a lot of things. One being reduced power. Now, if you throw like a P0102, that's a MAF circuit code. So you got a problem with the circuit. You wired it wrong, you got the wrong MAF sensor, something like that. If you get a P0101, MAF irrationality, and there's some others, P0060, I think, what that's saying is the airflow going through the MAF does not match what the computer is calculating based on throttle opening, throttle position, accelerator pedal inputs, and map sensor readings and other functions. So it will then put you into reduced power mode based on an airflow irrationality. And what I notice is some of these guys that are using homemade air intakes, and they're placing the mass sensor in the wrong place, they're placing the scavenge tube in the wrong place, they're getting not only MAF irrationality codes, and sometimes they're not getting that, but what they are getting is less performance, less economy, and less power, because while the system is adapting to their setup, it's not optimal, and they don't know it. When a MAF sensor is set up properly and it is feeding back correct information to the ECM for proper fuel control, it's amazing. It's just amazing. I mean, you can see that I think the furthest out we've gone here is 2% on this long-term fuel trim, and the long-term fuel trim is the indicator of airflow versus fuel delivery. If we're looking at it at 0 right now, which is perfect, obviously you can't get better than that. If you were going to see that at 15-20%, that's going to be a problem, and you've probably got a problem with your airflow, your air intake. You want to have that MAF in a 6-inch section of pipe that's straight. You don't want it in a curve. You don't want to mount the MAF sensor upside down so moisture can accumulate in the sensor or the hot wire. In the old days, we had what were called MAF burn-off circuits, and that wire would get really hot and burn all the contamination off. But that was a nightmare in itself. So they don't do that anymore. So you might want to check your MAF every once in a while to make sure it's clean. Don't just spray it with carb cleaner. You're going to ruin it. Use the proper manufacturer recommended procedure. Some of them will recommend a MAF cleaner. Some won't. They just want you to clean it. But it's really important for that MAF to be accurate, because if it's not, you're going to have problems. So that will also put you into reduced power mode. And I think what all this is boiling down to is technology is great, and if you look at a 1932 Ford, it can do exactly what I'm doing right now, and it would probably do it very efficiently. The question though is how far do we want to let these electronics go controlling our systems? And I think that there's a balance between efficiency, reliability, safety, and functionality. We don't want to lose OE functionality. We want to run all the factory supported modes. So like if you want to go into cruise control mode and use your tap shift, we want to keep that there. Smart charging, etc. So I think that's enough. I'll follow this up with another video on reduced power modes and some of the functions that we have in our newer modules. Thanks.